Okay, so we're going to do the notes and examples for section 2.5, proving statements about segments. One thing I do want to recommend with this particular lesson is that in order to work the problems, you need to have your chapter 2 notes. You also need to have your chapter 1 notes. So when we are proving statements, unless you have all of our vocabulary, postulates, and properties memorized, you're going to need to have the chapter 1 notes as well as the chapter 2 notes there in front of you so that we can use all of this information during our deductive reasoning process. So we have to use all of our known facts, definitions, properties, and postulates in order to prove statements about lines. When we look at the chapter 2 notes that we've been going through for several days, when we get down to section 2.5, there's not a lot of information here. So one thing that's here is different types of proofs. The most common type of proof that we're going to work is known as a 2-column proof. So in a 2-column proof, you'll have one column for the statements, and then your next column will be for the reasons. So we'll have a set of numbered statements, and for every statement we give, we must provide a reason. So we'll have a set of numbered statements, and we'll have a reason for each one. And keep in mind that all of this has to go in a logical order. So remember from section 2.3, our reasoning laws. So remember our reasoning laws, especially the law of detachment. We're going to know a piece of information. We're going to identify our postulate, property, or theorem that has that information in order to get its conclusion. So we're going to take a known given fact, apply some sort of postulate, property, or theorem in order to get a new fact. We'll look at a couple of other ways to write proofs in a moment. There is also what is known as an indirect proof, and in an indirect proof, you assume what you're trying to prove is false. So your first step within this particular proof is to assume what you're trying to prove is false, and then you work backwards to show that that can't work with what we were given. We're not going to do any indirect proofs in geometry. You do need to realize you're going to have a question here and there about how you should start one. So we're not going to actually do any indirect proofs, but if you were to start an indirect proof, your very first step is to assume what you're trying to prove is false. We get one theorem. It's the properties of segment congruence. So a couple of our properties from algebra will also work for congruence. It just so happens that the reflexive property, the transitive property, and the symmetric, so reflexive, symmetric, and transitive properties will work for congruence. So these three properties right here, so these three properties, the reflexive, the symmetric, and the transitive, are also true for congruence. So these properties work for equations, and they work for congruence. None of the other properties that are listed there work for congruence, just these three. So the reflexive, the symmetric, and the transitive properties work for congruence. So this is what that would look like. So our reflexive property would simply state that a segment is congruent to itself. The symmetric property would simply state that if we have a congruent statement, then we can switch the order of that. So if we have a congruent statement, then we can switch the order of that congruent statement. And our transitive property would say if I have a congruent statement and one piece of that congruent statement is congruent to another segment, then I can create a third congruent statement. So because my segment CD is congruent to both segment AB and segment EF, I get a new congruent statement saying that those items are congruent to each other. So if you are congruent to the same segment, then you must be congruent to each other. So if they're congruent to the same segment, then they must be congruent to each other. So pay attention to our difference between these three. The reflexive property is simply saying the same thing is congruent to itself. In our symmetric property, we simply switch the location of our segment names. And our transitive property, you have to have two segments congruent to the same segment, and then you can get them congruent to each other. Of these three properties, the transitive property and this reflexive property are the two that we're going to see the most often. So when we look at proofs, there are actually three different types of proofs. So we have this particular question. So this is our problem. In a proof, you will always have a set of given information, and we usually mark that on a diagram. So I have marked the 8 that was given for DG. We have marked the 8 that was given for GF. And then things that are congruent, we put the same slash mark on. So the GF and the EF have the same identifying mark. And then I always go in and try to find what it is we're trying to prove. What you're trying to prove will always be the last statement. So whatever it is you're trying to prove is your last statement. And within the proof itself, we will have our given information. So we're always going to have our given information, and then whatever it is we're trying to prove is there. So this is three different ways to look at it. So a two-column proof, we go through a set of properties. We also have what is known as a flowchart proof. So if you will notice how this matches up with the two-column proof. So my three pieces of given information are all at the top. So all of my given information is at the top. And then I draw arrows saying what they can lead me to. So my two pieces of given information with the equal 8 give me a new statement. That particular statement, using the definition of congruent, can give me another statement. And then my third piece of given with my newest statement will get me to what I am trying to prove. So underneath each line is its reason. So the statements are in boxes and the reasons are underneath, and you have arrows showing which statements lead to the next. So instead of having them in a column, you have the boxes that lead to the next. Now, The last type of proof is a paragraph proof, and I will not ask you to do a paragraph proof. And part of it is kind of selfish on my part because I really don't want to read through them. Also, they're a little more complicated to write because we have to explain things in a nice flowing sentence fashion. So we're going to concentrate on 2-column proofs and flowchart proofs. All right, so keep this set of notes handy, and we're going to look at some example problems. So keep together the information about our different types of proofs. So we are going to concentrate on doing 2-column proofs, and we may occasionally also be asked to do a flowchart proof. So here is our first example. As we're doing proofs, it's very important that you mark diagrams as you're going. So we need to understand how and why we're marking diagrams. This very first question tells us that N is the midpoint of segment PQ. So in my diagram, N and segment PQ are the information here at the top of this picture. So what we're going to do is we need to know what midpoint tells us. So I'm going to go and look up the definition of midpoint. So we learned about midpoints back in chapter 1, and we got the definition of midpoint in section 1.4. So a midpoint is a segment that bisects a segment into two congruent pieces. So our midpoint will bisect, which means that we divide into two congruent segments. So what I need to do on this diagram is I need to mark which two segments are congruent to each other. So it's the two segments on each side of N. So I'm going to mark PN and I'm going to mark NQ with the same hash mark. So I'm going to mark that PN is exactly the same and congruent to NQ. So it's the markings on the diagram that we need to do to complete this problem. So my next one doesn't have any special symbols that I need to look up. It says that the length of AC is equal to the length of BD. So when I look in the picture and I find AC, and then I look in the picture and I find BD, I see that they have some overlap information. So when I am marking a diagram where there is overlapping information, I actually do the markings outside of the picture. So I draw in where AC is located, and I draw in where BD is located, and then I'm going to put the same number of dash marks on them. So I identify where the locations of the segments are, and then I put the same number of slash marks on those segments. So we need to know how to mark a diagram to help us locate things as we're doing proofs. So before we actually start doing proofs, we're going to take a moment to try to fill in statements and reasons using some of our facts from chapters 1 and 2. So we have all of these postulates, properties, and theorems within our notes. So we have all of these postulates, properties, and theorems within our notes. So I'm going to shrink this just a little bit so that I can have access to my notes. So in the first problem, number 3, we're given the statement that Ln is equal to Lm plus Mn. So we have an addition problem. When we have an addition problem, I start looking at a couple of different places. So I'm going to check to see if this is my addition property. According to the addition property, I had to have an equation before I got the addition, so that one doesn't work. So my addition problem there doesn't work. When I look back, there are addition in the distributive property. So I have addition in the distributive property, but this one has no parentheses, so that didn't work. Keep looking back in chapter 2, and I don't see any other addition problems. So that means I need to go to my chapter 1 notes. And I'm looking for addition problems in my chapter 1 notes. So section 1.1 is all about naming segments. 1.2, I have an addition problem. If I have a segment where a point is between two others, then I can create an addition problem. So when I look at this, if I were to draw out the segment, my L with my N, and then I could put M inside, and this would be my whole thing and my sum of the parts. So these are the pieces of the segment addition postulate. I have a segment that was divided into pieces, and I added the parts to equal the whole thing. So this is my whole thing, and it's equal to the sum of the parts. So that's what it takes to do the segment addition postulate. If I have a segment in pieces, then I can add the parts to equal the whole thing. So my next question has a statement that the length of AB is 5. I have an addition problem of AB plus CD equals 10, and this is given information to me. And then my next line now says 5 plus CD equals 10. So once again, I'm looking at my addition. So since I'm already here and this is segments, we check to see if this meets my segment addition. So when I look at this problem, this is not part plus part equals whole thing. There is nothing to indicate that this is two parts of a whole. AB and CD would not go together. So I don't have a common point between these. So this is not segment addition. When we look back at chapter 2, this seems to be like we're working with an algebra calculation. And so we have this whole list of algebra properties. So here's one that says, if I have two items that are equal, then I can create an addition problem to both pieces. But when I look, here is my two items that are equal, but I did not add the same thing to both of them, so it's not the addition property. My next part that I can look for is I can always check substitution. Substitution requires that I start out with an equal statement. So when I look, I start with an equal statement. Substitution usually will also work with some sort of calculation that has one part of that, and then we are going to replace. So if we look, I have the AB, and I am replacing that with 5. So I'm taking my AB from my calculation, and I am replacing that with 5. So whenever I replace a part of a calculation, this is substitution. So this is substitution. Problem 5, our given information has a word, and anytime your given information has a word, my recommendation is to start with the definition of that word. And we got the definition of midpoint back in section 1.4. So midpoint, by definition, is a point that bisects or divides a segment into two congruent segments. So by definition, I'm supposed to divide into two congruent segments. And when I look at my next line, there's the two congruent segments. So these two congruent segments are actually stated in the next line. So this is applying the definition of midpoint. Problem 6. When we look at problem 6, the change up between these is that I have a congruence in the first part and an equals in the second part. I have a segment in the first part, so I have segments congruent, and then I have lengths. I hope if I spell that word correctly, wouldn't it? I have lengths equal. So I need to look and see if I can find any definition, postulate, property, or theorem that talks about segments congruent and lengths being equal. And we had a couple of different times where we talked about congruence and equals. Now keep in mind, this is talking about angles, but we don't have angles. So I need to keep looking back, and all the way back here in section 1.2, we have congruent segments, segments that have the same length. So here is a definition that has both of my parts. It has the congruent segments that I was given, and it has the equal lengths, which I created. So because congruent segments by definition have equal lengths, this is the application of our definition of congruent. Problem 7, this time we have to fill in our statement, and they're telling us to do this using the definition of midpoint. So remember that we talked about this one previously. Our definition of midpoint is that we're going to divide into two congruent segments. So my statement here is going to be to tell which segments are congruent. When we're dealing with a midpoint, we have our first end to the middle will be congruent to the middle to the other end. So from the first endpoint to the middle is congruent to the middle to the other end. Problem 8 is very similar to problem 6. We have two lengths that are equal, and then we have two segments that are congruent. Now, we don't have a definition of equal lengths. We do have a definition of congruent segments that talks about equal lengths, and this is where you have to remember that definitions work both ways. So if I know the lengths, I get the congruence, and if I know the congruence, I get the length statement. So problem 6 and 8 actually have the exact same reason, even though the statements are in opposite orders. So this is still the definition of congruent. We don't even have a definition of equal. The definition of congruent is the definition that has these two parts. So this is the information that has what I was given, and it has what I'm stating. So our reason should contain everything we have. It should have what we're given in the if portion and what we're saying in the then portion. Our last one that's here is where we're given two equal statements and we get a new equal statement. So this is not congruent. The congruent symbol is not there anywhere. There is no addition. There is no calculation. So when we get a problem that looks like this, we want to go to our algebra properties list and we want to look at these three properties: the reflexive, the symmetric, and the transitive. These three properties talk about things that are equal. So it's just a matter of how many things we have that are equal. Be careful, we're not using substitution. Substitution is replacing within a calculation. So this one is where we're replacing within a calculation, but we don't have any calculations here. So we're looking at reflexive, symmetric, or transitive. Our reflexive property is one statement, no previous information, and it's just the same thing. So that's not what we have. Our symmetric property, we would have one equal statement in our given line, and then we would just reverse that in our second line. And then we have the transitive property. It says if I have two equal statements with some matching information, then in my next line, I get a new equal statement. So if we notice my KL from the first equation, then I have a repeated value of MN, and then there is the OP from the second equation. So this is a matter of where they are equal to the same length. So they're equal to each other. This is our transitive property. All right, so this is quite a challenge and quite a task. So you're going to need to practice with using your notes to identify statements and reasons. So now we're going to put that together and we are going to use all of our information in order to complete the reasons for a proof. When we're looking at completing a proof, we always need to start with what we're given. And you're going to notice that we have a couple of different given pieces. So we are given this midpoint statement, and then we are given this equal length statement. Whenever I have a proof, the first thing that I'm going to do is I'm going to go through all of my statements and try to locate those. So in line 1, I have one of those statements, so I know what my reason's going to be. And then in line 4, I have that other statement. So these items have been given to me. So this information was given to me. I don't have to look for a reason other than they gave it to me. So all of the given information, your reason that it's written down is that it was given to you. So we were given that this X is a midpoint of MN. So my X is in the middle of M and N. And we were also given that MX is equal to Rx. So I'm going to mark them with the same thing. Now, the other thing about a proof is whatever it is we're supposed to prove will always be the last statement. However, this last reason is never anything to do with the word prove. So you're never going to say that the reason for this is prove. So this is not a reason. This is our task. So this should never be a reason. So our reason is never the word prove. Prove is our task. It's not our explanation. All right, so now we're going to rely on information. So our first piece of given is that word midpoint. So we go back and we either have it memorized or we find our definition for the word midpoint, and we see that the definition of this word says that we divide into two congruent segments, and our very next line happens to be the two congruent segments. So our MX and segment XN being congruent is our definition of midpoint. Between the next two lines, our change is that we go from having a congruent symbol to an equals. Anytime I go from having a congruent symbol to an equals, so I went from a congruence of segments to lengths being equal. This is our most common vocabulary. This is one of our most used vocabulary words. We're working with segments, and we're going from congruent segments to lengths that are equal. So this is our definition of congruent. Our next piece of information was given to us. And then all of a sudden they say we're now ready to finish the problem. So we're at a bit of a conundrum. Why are we suddenly finished with the problem? And usually when that happens and you have a series of equations that are equal, go back over here and check out these properties. The symmetric and the transitive property usually involve taking equal statements to get an equal statement. So my line 4 and my line 5 both have Rx in them, but I'm changing up my Mx, which happens to be also in the previous line, and I'm replacing it with the Xn. So I'm taking my Xn from line 3, my Rx from line 4, and they're both equal to the same thing. So this is my equal to the same value. So this is our transitive property. So that last line has to be a definition, property, postulate, or rule of some sort. It can never be the word proof. So here's another one. We have a diagram. We are told in our given that T is the midpoint in this particular picture. So I find that, and I automatically know that the reason for that statement is because it was given. I'm also going to put point T on this particular diagram. My next line tells me that I'm supposed to use the definition of midpoint, which means that I'm going to divide into two congruent segments. So this line is going to be the names of those two congruent segments. So from my first endpoint to the middle is congruent to the middle to the other endpoint. From line 2 to line 3, I'm going from a congruent statement and changing it to an equals. So congruence to equals is our most common vocabulary word. So going back and forth from congruence to equals is this same congruence definition. So anytime we switch back and forth between those two symbols, we are working with our definition of congruent. So from the congruent symbol to the equal symbol is our definition of congruent. Problem or statement 4 is one of our more challenging pieces. I suddenly have an addition problem. So I start looking at my addition things. And when I have addition, there's really 3 pieces that I look at. I look at the addition property. So did I have something that was equal and I added an addition to both sides. Well, I have AT equals TM, but I didn't put the same addition on both sides, so it's not that one. The substitution property can also work with this, but I have to have an existing addition problem and I just replace. So the substitution, if I already had an addition problem and I replaced a part of it, and then the third place I look for an addition is in a postulate that actually has the word addition built right in. So if I have a segment between, or a point between two others, then I can suddenly create this addition problem of adding the parts to equal the whole. Well, my point T is definitely between A and M, so I can take the first part and the second part and make them equal the whole amount. So if I add the parts, it should equal the whole, and this is an addition of the parts to equal the whole thing. So this is our segment addition postulate. In the next line, I am told specifically to use substitution. Substitution means that I am going to replace something in this calculation. So I have this addition problem and I need to replace something. And when I go to replace something, I want to keep in mind, what is it I'm trying to prove? In my final statement, I want the AT and the AM. So in my final statement, I want the AT and the AM of this calculation. So that means that I want to replace the TM. And from my previous line, I'm told that I can replace that with what it's equal to. So I'm going to keep the AT. I'm going to keep the addition. I'm going to replace the TM with what it's equal to. So when I replace, that's substitution. The next line that I have here is one that is not anywhere in our notes. All I've done is taken this addition problem and combined our like terms. So this is just a matter of simplifying a calculation. So this is none of our special properties. There's no rule, postulate, property, theorem, or anything. This is just combining our like terms to simplify the problem. And then in my last step, this times 2 has been removed, and I now have a 1/2. So when I go back and look at how to remove a multiplication, so I need to remove multiplication. We talked about removing calculations in the algebra properties, and we talked about how the division property can be used to remove multiplication, and how we could also use the multiplication property to remove multiplication with fractions. So this one can actually be the division property or the multiplication property. I'm going to tell you it's going to take you some time and effort to complete proofs. Until you have your notes memorized and know where to go and find things, they're going to be a time-consuming process. So take your time, use your notes wisely, and complete.